Welcome back to Physics 151 Online. Now that we've defined potential energy and we know how to calculate potential energy as minus the work done by a conservative force, we can turn that relationship around and come up with an equation to solve for force in terms of the potential energy function. And so let's consider, for the simplest case, an object that moves only along the x direction. Okay, so if we want to find, using the definition of potential energy difference delta U is minus the work done by a force as it moves along the x direction from an initial to a final position, right? And we realized, of course, that when you add up small quantities using an integral in calculus, you're summing up infinitesimal quantities. And so this first equation is really just a definition of what we mean by a change in a function like potential energy. So it's the integral of du. We know by definition that that's minus the integral of the force dx, because that's the work done. This integral is the work done. And then if we just put that minus sign into the integrand, we can look at the expression that has the integral of du, and then the final equation which has the integral of minus f sub x dx, and we can identify those two together, right? Because if those two integrals are equal to each other, then the integrands have to be equal to each other as well. So a small change in potential energy is equal to minus the x component of the force times a small change in position. And just solving that for the force, we find that the x component of force is equal to minus the derivative of potential energy along the x direction. And if we had a potential energy function that depended on x and y and z, then a similar kind of equation would give us the force components along the y and the z directions as well, except in those cases the derivative would be with respect to y and z. But this equation is actually quite useful, especially if we want to understand qualitative behavior of an object that has a certain kind of potential energy function that it's subject to. So here's the case of a spring, right, where the potential energy function is 1/2 times a constant k times x squared. So you've got this nice parabola, and we have to consider both sides of the vertical axis, because positive x means the string is being stretched, negative x means the spring is being compressed. And so if we recognize that we've got this parabolic potential energy function, we can use the definition of force as minus the derivative of the potential energy to analyze what's going on to the object at different points in its motion. So at x equals 0, which we know is the equilibrium position, the slope of this curve is 0. And since minus the slope is the force, we know that at x equals 0, we are at an equilibrium point. The force is equal to 0. That's what equilibrium means. Force equals 0. Now let's consider, what if the object the object connected to this spring moves a little bit in the negative x direction. So the spring is being compressed. What does that mean? Well, at that point, the slope of the potential energy function is negative, and minus a negative is a positive. So this means qualitatively that for negative values of x, the force is in the positive x direction. See? And then we can consider the same thing on the positive x side. If the spring is stretched now so that x is positive, then the slope is positive, and minus the slope then would become a negative value. So for x greater than 0, the x component of the force is less than 0, which means that the object experiences a force that pushes it back toward equilibrium, right? And as a result, because we've determined that a small displacement in the negative x direction produces a force back toward equilibrium, and a small displacement in the positive x direction produces a force back toward equilibrium, we now know that at the origin, not only is this object in an equilibrium position, but it's a stable equilibrium position, because any small movement to the right or to the left causes it to experience a force that restores it to equilibrium. Of course, there are other kinds of equilibrium points, because all that equilibrium requires is that the slope of the potential energy graph be equal to 0. So you can imagine a more generic kind of potential energy function like this, and then think about what's going on at different points along here. Of course, at the bottom of the trough down here where the potential energy is a minimum at point D, the slope is equal to 0. And you can just see by inspection that moving to the right or to the left will produce a force that pushes the object back toward point D. So that's a stable equilibrium. And if it helps, you can just think of this red curve as a hill of some kind, and think of a marble that would move along that direction. If it was at the bottom of the hill and you just pushed it to the right or left, then it would roll back down toward the bottom. So that's a stable equilibrium position. What about point B? That's still an equilibrium point because the slope is equal to 0, therefore the force is equal to 0. But, for example, let's look at a small displacement of the object away from point B towards point C. So if we move to the right from point B, the slope of the curve is negative, minus a negative is positive, so the force is in the positive direction. And so what you show is that a departure from equilibrium causes the object to experience a force away from equilibrium. And that's the hallmark of an unstable equilibrium point. So point B is unstable even though it's equilibrium. And then point F, that's more of an unusual case, but imagine that the curve flattens out at a certain point so that the slope is equal to 0. Well, that means it's equilibrium, right? Because the slope is equal to 0, so the force is 0. But if you push it a little bit one way or the other, it doesn't experience any force at all. So if you push it to the right with a certain speed, then it will just continue moving to the right with a certain speed. It won't return to equilibrium, but it doesn't pick up speed either. And so that's called a neutral equilibrium point. So these are qualitative considerations that arise from the definition of force as minus the derivative of the potential energy function. And so you can get useful qualitative information about the motion of an object if you know what its potential energy graph looks like. So I hope this has been a helpful addition to our understanding of the relationship between force and potential energy, and I will see you in class.